Hello everyone, welcome to the second video on this channel, Bad at Physics. Today we will be looking at progressive waves from the Physics 9702 CAIE International AS level. Now, we can define wave motion as the transfer of energy without the transfer of any net matter. And here is what the layout of a wave looks like. So we can trace this wave, and this is called the equilibrium, which is the x-axis. Now, we have basically our amplitude right here. Specifically, this is the crest. Now, the crest is the positive maximum displacement from the equilibrium. And the trough here, which I've labeled as number 3, is the negative maximum displacement from the equilibrium. The wavelength is this little spot and this little spot. Please do not confuse them and try to draw a spot from here to here and stop here, because that would not be a complete oscillation. It's defined as the distance between two successive points of a wave that is, most importantly, in phase. Now, we may also be asked what a period is. A period is the time taken for one whole oscillation. Basically, you can try to get it by rearranging for t to get the time period, which in this case would be 1 over frequency. And frequency is, if you might have seen a couple wave demos. So the higher the frequency, the more this little red dot moves around faster and faster and faster. It's basically the number of complete oscillations passing per second. Now, there's two types of waves that we need to be aware of according to the specification. The transverse wave, let's say we have a rope here. A rope can be used to demonstrate transverse waves. If I grab the rope and I start shaking violently, the particles in the rope will move up and down. However, the oscillations of the particles in the rope as a whole will only move or be displaced vertically. They do not move horizontally. So it's only the energy transfer from the particles moving in the rope that moves perpendicular to the transfer of the particles vertically. Okay. The next type of wave we need to be aware of is a longitudinal wave. So the longitudinal wave is best represented by a spring, because in the longitudinal wave, the vibration of particles back and forth is what basically creates the energy transfer. And that energy transfer is parallel to the particles transfer. So if you grab a slinky and you start pulling it, you might notice that this area right here, where the waves are extra compressed, believe it or not, is called the compression. And these areas where the waves are not compressed and a bit spread out are called rarefactions. Right? That's the only difference between them. Also, they may ask about P waves and S waves, but a quick Google search will probably clarify that. The next part is a CRO, or a cathode ray oscilloscope. We don't really need to know what this thing is, but we do need to know how to solve them if they come on the past paper. The cathode ray oscilloscope, basically, it displays the AC signal. You can basically find your frequency and amplitude as well. If you're ever given, for example, you might be given a bunch of squares here and a key of how one square maybe like a centimeter, and you'll have like 5 little subsquares in here. You may have to calculate the time base and the Y gain. So the Y gain is also called the peak voltage. So you just want to count up the squares, right? You will be given little squares in the CAIE exam. You want to count up those little squares. And you want to divide them by whatever you want to find the whole length of this square first. And then you want to divide them by the number of tiny squares inside of them. I will do this in another video coming shortly on past paper questions. And you'll have to do the vertical divisions times the Y gain, which is usually provided on the question itself. However, a much trickier one, I'd say, is finding the time period, because some people will forget to use the frequency is equal to 1 over the time period formula. They'll just do this and be like, oh, that's it. So time period, again, you do the same thing. You count up how many little squares are in, like, let's say that we're asked to calculate the frequency, right, of this line, of an imaginary line here. So we would count up these tiny little boxes inside each square, and then we take that and we divide that by the key. So if this one box is 1 centimeter, we're going to do 1 centimeter divided by, let's say, there's 5 tiny square boxes. So we're going to have 1 over 5, that's 0.2, and we're going to have 0.2 times the time base, which will also be given. And then after that, once we have the time base, to find the frequency, we do 1 divided by the time period. Now, the remaining part of this is we have to know the properties of a progressive wave. The progressive wave does not transfer matter. It only transfers energy. And oscillations carry energy. Particles do not move whatsoever. Like, you will not find a rope sliding out of itself to transfer the energy when you shake it up and down. That's just not physically possible. The next part we need to know is the intensity. The intensity is defined as the rate of energy transfer per unit area. And it's given by the formula that the intensity is equal to the power over the area, which we can further break down into their units. So if we have the power, which has a unit watts, and we have the area, which has a unit meter squared, we will know that the unit of I is equal to watt meters negative squared. And that is the unit for the intensity. And we need to know that intensity is directly proportional to the area squared, or the amplitude in this case. Sorry, that is not area squared, that is amplitude. So there's a few factors that affect intensity that we need to know. So the further the distance from the source, the more the intensity decreases. So think of it this way. If I have a flashlight, okay, it's a very poor flashlight, and the intensity just keeps spreading out. I know that's a horrible drawing, but the intensity is strongest in this region where these rays of light are closer. The more they spread out, the weaker the intensity becomes. Sorry, just need to get rid of the flashlight. Now, we should also know that the amplitude, greater amplitude means that there's higher energy, and the higher energy means that there is, I need to catch myself there. It means that there is a higher intensity. Now, we also need to know that any absorption from a medium weakens the intensity. It's like trying to shine a flashlight through a body pillow. No light, a little bit of light may come through, but it will be probably a tenth of the intensity of the original ray of light. And that is all for the progressive waves, unit 7.1. A past paper video, or possibly 7.2, will be coming out tomorrow in quick succession. I plan to work backwards and cover the whole course.